So I'll start with a little bit of myself. So I was trained as an architect and very passionate about during my studies and practice. I became very interested in the digital technologies and the power that it brings to us as designers. So, for example, the different quality of space when we combine digital space and physical environment, and also the making, the new possibilities that it can bring back to some old construction methods. And here are some of the teaching outcomes we used to achieve at MDIT. Lawrence and Jeff will remember this structure. That's in the sound studio. So here are more teaching outcomes from the digital fabrication stream. So we make really complex things using the digital fabrication and computational design tools. And professionally, I was able to upscale this in some large projects. That's a facade public art project at Brisbane, CBD, won through a design competition with a partner, Alex Knox. So that's a little bit of introduction. So basically, I became very obsessed with the digital tools and all the possibilities that it brings. I feel very empowered. I can almost make everything until I started working to the next stage and constantly get asked the question, like, why? Why are we doing these things? It's cool. So I also want you to, as young designers, to start thinking, well, we can almost build anything, but should we? And what are the meanings behind the things that we make? As we touched on earlier, circular economy is important, and as you know, globally we're facing a lot of climate challenges, and some of the quotes are actually indeed quite scary, like we don't have much time left to fix anything if we can fix it. And being an architect, I'm very responsible, as the building industry is heavy contributor to all these problems. Yeah, we generate a lot of energy consumption, put a lot of waste into the world. And sometimes the digital technologies can give us ability to design amazing buildings, good for the humanity. But once you start thinking the making process, you realize, wow, to make something complex, that's always, it could lead to a very wasteful process, like one-off formworks, for example. Here's some recently finished building by Met Architect in China. It's a fantastic building, absolutely amazing. But if you dig deeper, you start questioning some of the decisions. For example, here you can see the construction company or the architect decided to almost build the building twice. You build it in timber, cast it in concrete, and you throw the timber version away, or in landfill, I assume. Even with some of the advanced digital design techniques, for example, topological optimization, which is meaning to take away of material to increase the efficiency, so you save material by using less. But if you look at the making, still, that's always another layer of complexity and waste associated with making these things. So my personal research, yeah, again, like almost with digital industry 4.0 and digital technologies, we can almost make anything, like absolutely anything. But should we? So my research looks at the intersection between computational design, digital technologies, and how these tools help us to work with the principle of circular economy and try to keep doing cool things that we like to do, but in a more responsible way. I won't go too deep since it was very well covered, the Cradle to Cradle book. So basically, circular economy just promotes, instead of the linear take, make, waste, we're trying to keep everything in the loop, reuse, repair, and relook at ways to bring second life to them. So how do we do this using the technologies that we have. So particularly I looked at upcycling and biofabrication, and today I'll focus on the upcycling part. So computational design and the modeling tools that we use, it's a very powerful tool. It allows us to work with a lot of constraints and deal with the complexity in a systematic way. For example, this is a student class project at Swinburne, where students were tasked to make an installation for the void of the building using cable ties. So they were tasked to take into the consideration of the cable tie structure constraint and using the computational system to manage the complexity. So as you can see, the digital tools really allowed them to very efficiently manage those material constraints and were able to use that simple elements of cable ties and create a fairly sophisticated structure. And that's another examples using recycled bike spokes. It was again a student project back at Melbourne University that I taught, where students looked at designing a canopy using bike spokes that's been thrown away, and using some simple 3D printed joint to reconstruct them into structural elements where they're all connected and linked together to form a canopy. So then we know now, we discuss the computational tools thus give us the ability to work with material constraint, which is very useful for the case of upcycling. But as an architect, we always try to build things bigger, and we're starting to run into troubles. We can't have a design project assigned to us, commissioned to us, and then go around in the park and trying to find rubbish. It's not very strategic. So the next level of thinking is then, well, are there ways for us to set up a system where these type of thinkings can be upscaled? So particularly, we change our focus to looking at industrial waste, and I'll use two projects to demonstrate that. So in this particular pavilion, with Jane here being a part, we looked at the plantation industry in Australia, the timber framing industry. So in each tree, the issue was once they harvested, you have to get rid of the knot within the tree, and you can never tell where they're going to be because it's nature. Sometimes it's this location, sometimes it's a bit lower. So only when you chop off the knot, you get the good length. They become commercially valuable to be sold for framing. But then the problem is you always end up with a bunch of short length and random length timber that has the same structural integrity, but just because it's hard to work with, it's usually being wood chipped or burned as waste. So with the material, we then think about, well, how can we design with this very particular material? So it was a competition in Barcelona, so we thought we'd pay tribute to Gaudi by employing the hanging chain method. And we looked at each of these waste. We have a library of waste inventory, and we developed the algorithm where through the tangential matching, the computer will search through what's available and try to match it as much as possible to our desired form. Here's a demonstration. Taking this principle, then we started to work with the pavilion design itself. So as you can see, that's the form that we desired, and now we run through the search in the inventory, the random length timber that we have. The computer is trying to do the best it can to match using the heuristic search, like first fit, first available. And you can see that's always going to be a little bit of a difference, because once what we design, once what's actually available. But then you can see they never actually match. But the difference is small enough, so then the computer can then take the results of its searching and re-simulate the form, and this time the darker form that you can see here is using the exact amount of the waste that was available to us and reconstructed the whole pavilion form. And the rest is about the detailing. How we're using lap joints and a little bit of a groove channel on the top of the each beam for cladding, and all the complex nodes were broken down into planar surface, planar element, which can be easily machined using 3-axis CNC machine. You can see here's a detailed image. And the pavilion was then put into a few suitcases and boxes and traveled to Barcelona with us. And another principle in circular economy is designing for disassembly. You always design things with mechanical joints which can be taken apart and reused. So the pavilion survived in Barcelona and was later brought back to Melbourne for another exhibition. So that's a picture of the pavilion in Barcelona. And then it was brought back to Melbourne University for the future prototyping exhibition. And then after that, it was again sent to Queensland for another exhibition. So it's a very well-traveled pavilion indeed. So that's a smaller scale. So as we progress, we keep thinking, well, can we upscale this and turn it into something that can even go beyond a pavilion, standalone pavilion's structure. So I'll show some of the tests that we are trying to push in this line of thinking. So in this next project, we were working again with the Australian timber plantation, which is grown in Hervey Bay in Queensland, using recycled water. So the company is called White Bay Water. So they take all the recycled Class B recycled water from local business like household and the shops, and then they process the water, and instead of ejecting those treated water into the ocean and pollute it with chemicals, they redirected the recycled water to grow gum trees with plantation. And the plantations are very good at going through a small period of drought. So when local farmers need the water, they can always direct the water and sell to the farmers. And when the farmers don't need it, they will use the water to irrigate the plantation of the gum tree. Here's a picture of the plantation. So the issue they have was, so in plantation, at the beginning of the planting of the trees, they try to plant them in a really tight grid so that they force the trees to shoot up really high to compete for sunlight. So at year 10 to 18, they will go through a process called the plantation thinnings, where they will go in the forest, identify almost every second trees that aren't growing very well, the thin ones, and chop them away to give a space for the rest of the healthy tree to grow in diameters. So I think the criteria was the tree has to reach around 250 millimeters in diameter at roughly 15 meters height. That's when it's deemed to be usable for future harvesting. The rest, again, no one knows how to use them. No one wants to buy them. So they always lose money. The plantation's losing money just to get the workers to come in and remove the tree. And you can see that there's some of the quote from them. It's being sold at $1 per 6 linear meter. It's basically almost rubbish for free. So here's what they look like, the thinnings. So again, based on this very unique product, we then tailored our computational design approach for us to be able to utilize this very unique material. So here's the computational demonstration. So we decided to design a truss structure branched structure. So then again, it's a flexible system where it will, with a given length of tree, the algorithm would distribute the length over this branched structure and always try to match the exact length. So then that gives us a chance to work with whatever tree we were given to. So we were given a chance to design a demonstrator in the Queensland State Library. That's the site. And we on purposely decided to use a very regular roof grid on the top in hope that if the prototype works, we could potentially try to reimagining in a more non-pavilion typology, connecting with regular roof, walls, etc. So here's a scale model before we build it. So again, the algorithm was further refined, so then the algorithm will always snap the endpoints of the truss structure to the given grid and also match the tree length that were given. And then it will go through a process, a structural optimization process, where the weight of the roof grid and the self-weight of the branches will be embedded into the computational model, and the model will keep the design but shift the nodes to achieve a structurally more efficient form. So here you can see that's a little adjustment based on the weight and the structural analysis under both tension and compression. And it then is further verified in structural simulation tools. So here's the fun bit. So we decided to push the project to extreme, and we did a real-time test. So one morning, one of the team members went into the forest, Kim Baber from Queensland University. They identified a few trees and chopped it in the morning, those thin ones. And then he sends me a few text messages where I'm in front of the computer, nervously waiting. So these are all the information that we needed: tree B, the length, diameter. And I was working with Joe Geddes, a structural engineer at Queensland University. Real time, we're updating the script. It was very nerve-wracking because we always worry about what if we make mistakes. One little calculation that's wrong, nothing will match, and then we waste a few trees. It was actually very scary because I did find a little mistake in my script, which made me nervous for a few months until the pavilion was built. So in the morning we received the information, we update the script using those information, and in the afternoon that's all we send back. An A4 piece of paper telling the guys where to cut and where to mark. And then that's them in the afternoon, rushing us. The sun's going down, it's dangerous to use the chainsaw. Can you guys hurry up? Yeah, it was quite nervous day. So you can see. And the taller run was built in. So we have it will be absorbed in the node structure. So it's okay for him to be a little bit rough with his chainsaw. But roughly, the length was correct. So it's all done in one day. And then it was transported through a car. Once they chop in smaller pieces, it's very easy for transport. And the next challenge is the node design. So given this structure, then the tree, depending on the length and where it's chopped, it will always have different diameters. So then the next challenge is how do we develop a connection method where it can take in all these different diameters to match them smoothly and nicely. So we developed some a mesh smoothing algorithm where we can use some very simple quad-based mesh connecting to the different diameters and smooth it afterwards to create this transition. So you can see that's the outcome. And then each of these nodes, they look very complex, but we were able to break them down into pieces that can be laid out flat. Again, easy for fabrication. So here's the component, a breakdown of it. So you can see every one of these pieces will have a planar edge that can really easy to be laid on a flat table. So then we thought, oh, we should push this even further. Why can't we use recycled material for the node? So we decided to, we were donated with some off-cut LVLs, again, short length timber for the node. So we match every single one of these segment onto this LVL node, which ranges between 600 to 800. I think the max would, they say, don't go over 1 meter. And yeah, so every node was constructed with this LVL and then smoothened later. I will show in the next few slides. And for the connection, we tested different methods, whether timber dowel, with screw, without screw, plywood connection, and the conclusion was the timber dowel with screw was sufficient enough for the self-weight. So here's the node that I mentioned that was built with recycled LVL offcut. So they were first glued together and then chopped just by a little bit. So then in the later machining process, we're not cutting a whole large chunk of timber, but just a little bit of sculpting. Again, try to minimize the waste involved in the process. So here's the scale of the node. So you can see it's about this size. And very interestingly, the fact that we were using the LVL as a donated material also give us a very unique sense of aesthetic. So the design aesthetic was also an element that we didn't really envision, which was a very pleasant surprise. And here's the construction process. The whole pavilion was built in 2 days, roughly 2-3 days. Just a few of us, all by hand, very easily put up and connected. And that's the final product.